settle in and let your breathing slow, as if the room has gently widened around you. Somewhere far above your ceiling, space is doing its usual quiet work, cold, dark, and endlessly patient. And in that dark, Venus hangs like a pale pearl behind gauzy curtains, bright enough to look harmless. You might think a bright planet means a warm, friendly world, but that is your Earth brain being optimistic again. Tonight, with the Sleepless Scientist drifting beside you, you are not here to survive. You are here to observe. The unbroken cloud blanket, the strange winds that hurry over a sleepy surface, and rain that falls, then simply forgets to arrive. Just weather, done the Venus way, slow and unreal, like a dream you can listen to. You drift closer, and the first thing you notice is not fire or lava or drama. It is the quiet geometry of light. Venus does not sparkle like a jewel. It shines like a well-polished bone. That brightness is not kindness. It is the planet holding up a mirror made of cloud and throwing sunlight back into space. From far away, your brain tries to map it onto something familiar. A bright world must have bright mornings. A bright world must have blue skies. A bright world must have weather that ends and starts and gives you little breaks. Wrong. Venus is bright because it refuses to show you what it is. It hides behind layers and layers and layers. Like a person who only ever texts back with one vague sentence. As you coast inward, you stop thinking of a planet with an atmosphere. You start thinking of an atmosphere with a planet trapped inside it. A thick, pale system of clouds wraps the whole sphere, almost unbroken. The surface might as well be a secret you are not allowed to learn. And you would take that personally, if Venus cared about your feelings. The top of the cloud deck is, by Venus standards, almost polite. Up here, the light has somewhere to go. The temperature is not trying to melt you into a memory. If you could stand on something, which you cannot, it might feel like a high mountain day on Earth, chilly, thin, and glaring. But do not get attached to that thought. On Venus, even the gentle places are only gentle because they are far from the truth. These clouds are not the soft, water-stuffed pillows you know. They are made mostly of droplets of sulfuric acid, which is a chemical way of saying they are made of regret. They look creamy and bright, like warm milk under a lamp. But if you could touch them, your glove would begin a long, miserable apology. The planet below rotates slowly, so slowly it feels half asleep. One Venus day, one full spin, takes longer than a Venus year. It is the kind of fact that sounds like a trick question. You picture the surface turning in syrup, lagging behind its own sunrise, and yet, above that drowsy ground, the clouds move with a different personality. This is the first strange weather lesson Venus teaches you. You can have a world where the ground barely bothers to turn, and the sky races anyway. You can have a place where the atmosphere behaves like it has its own schedule. On Earth, we blame the wind on heating, on spinning, on land and sea. On Venus, the wind feels like a decision that was made a long time ago and never reconsidered. But we are not chasing the fast winds yet. First, you hover at a distance where the whole planet is a single object, a bright disk, blurred at the edges by haze. but clouds have subtle bands and swirls. Not the sharp, proud spirals of a hurricane, more like long brushstrokes, slow motion, and a little tired. If you imagine lowering yourself into that cloud ocean, you start to notice the layers. Venus is a world of layers. Up high, the light is clean and cold. Lower down, the clouds thicken, and the haze grows heavier. The sunlight becomes a dim rumor, and underneath, hidden from ordinary eyes, is the part Venus does not advertise. This is where you remember why we are only here to observe. Because the deeper you go, the more the atmosphere stops being air and starts being weight. The air on Venus is mostly CO2, carbon dioxide, the same molecule that bubbles out of your soda and slips from your lungs when you exhale. On Earth, it is a trace ingredient, a background flavor. On Venus, it is the whole meal. It packs the sky with mass, with pressure, with insistence. You keep sinking, calmly, like a coin through honey. The clouds do not part to reveal a scenic landscape. They just keep being clouds. The haze grows dimmer, yellower, like old paper held up to a weak lamp. And as you descend, pressure builds in a way that is not dramatic. It does not slam into you. It does not roar. It simply accumulates. Every meter lower adds more atmosphere above your head. More gas stacked like invisible blankets, except the blankets are made of molecules that do not care if you can breathe. Near the surface, the pressure is like being deep in an ocean on Earth, not a gentle swim, not a sunny beach. The part of the sea where light gives up, the part where the water pushes at every seam, looking for weakness. On Venus, that crushing force is not water, it is air. You can picture it as a hand on your shoulders, not squeezing quickly, just leaning, relentless, patient. The kind of pressure that would flatten an empty bottle without effort, the kind that would punish any little pocket of trapped gas. If you tried to speak down there, sound would behave differently. Sound is just vibrations moving through a medium. Thicker medium, more molecules to bump into. So in that dense Venus air, sound could travel in a strange, heavy way, as if every word had to push through a crowd. Your voice would not feel crisp. It would feel muffled and close, pressed against your face. And moving through that air would feel wrong too. On Earth, air is a thin inconvenience, a thing birds use and leaves wave through. On Venus, air has the density to shove back. If you tried to run, it would be like running through warm liquid, not because it is liquid, but because it is thick enough to imitate one. Congratulations, you have discovered that a planet can drown you in its atmosphere. This is the part where people usually imagine the pressure as the main villain. They imagine being crushed. But pressure is only half the lullaby, because the same thick air that presses down also holds on to heat. You continue downward, still not landing anywhere, still just drifting in imagination. The light becomes a dull orange smear. The world grows quieter in a way that feels unnatural, like cotton stuffed into the sky. And then the temperature starts climbing and climbing and never finding a reason to stop. Venus is hot in a way that does not flicker. It does not have a cool evening. It does not have a breeze that resets the day. It is heat with no punctuation. You can blame the greenhouse effect And that would be correct. But the phrase greenhouse effect sounds charming. It sounds like tomatoes and glass walls and someone watering plants. On Venus, it is more like being locked in a car in full sunlight, except the car is the entire planet and the windows are a thick atmosphere that refuses to let the warmth out. Sunlight comes in. Some of it reflects off the clouds, which is why Venus looks bright, but enough of it still gets absorbed and turns into heat. Then that heat tries to leave as infrared light and the CO2 atmosphere grabs it and re-radiates it and grabs it again, like a bureaucracy made of molecules, endlessly stamping the same form and refusing to let it exit the building. So, the surface stays hot. Not the heat of a campfire that warms one side of you. Not the heat of summer asphalt that cools when the sun sets. This is heat soaked into everything, into the air, into the rocks, into the very idea of night. On Venus, the ground would feel like the inside of an oven that someone forgot to turn off. The rocks are not glowing red like lava, not necessarily. They are just baked, so thoroughly warmed that if you placed a metal tool down, it would slowly become the same temperature, like an object surrendering. Some metals would soften, not in a dramatic puddle, but in a tired sag. Plastics would not last. Electronics would struggle, then fail, then become quiet little lumps, and all of this happens under an atmosphere that is also crushing you. Because Venus believes in teamwork. Humans have actually sent landers here. Soviet missions in the 1970s and 1980s dropped down through the clouds and touched the ground. They did not explore for long. They did not stroll. They did not plant flags and pose for hopeful photos. They survived for minutes, sometimes a couple of hours, long enough to take pictures that looked like they were shot through thick, brownish fog. Those images are not the crisp postcard visions people want. They are low, flat landscapes with scattered rocks and a horizon that feels too close. Because the atmosphere is so dense and the light so filtered, the world looks compressed. It looks like a room you cannot fully see across. And still, even in that ugly light, you can sense the weight of the place. A planet pressing down, radiating heat upward, wearing its clouds like armor. This is weather, yes, but not the kind that makes you reach for an umbrella. It is weather that makes you understand umbrellas were always a luxury. The odd thing is, it is also boring. Not boring like uninteresting, boring like steady. No seasonal snow, no gentle spring, no monsoon drumbeat followed by relief. Venus has managed to make one of the most extreme climates in the solar system, and then keep it on repeat. You might expect storms to match the furnace. Towering thunderheads, lightning tearing through the haze every minute, a constant howling gale at ground level. But Venus, in its own slow way, offers something stranger. Down near the surface, the winds can be surprisingly mild, not because Venus is kind, but because thick air behaves differently. A slow wind in a dense atmosphere can still move a lot of force. It can still push. It can still carry heat around, but it does not need to scream to do it. It is like watching a slow river, quiet on the surface, heavy underneath. So you can have a world where the ground feels still, and yet the sky above is doing something entirely different. Because far above, near the top of the clouds, Venus runs its real wind experiment. Up there, the atmosphere can whip around the planet in just a few Earth days. It is called superrotation, which sounds heroic until you remember it is just air showing off. Imagine standing on a treadmill that moves fast while the room itself turns in slow motion. That is the feeling of Venus. A rushing ceiling, a lazy floor. The clouds circle and circle, painting the planet with moving patterns, like long exposure photography that never ends. You watch the cloud tops, and they look like a soft ocean viewed from above. There are bright streaks and darker swirls. The sun is a pale disk, filtered through haze, if you could see it at all. Shadows do not look sharp, they look tired. And now, very gently, we can talk about what those clouds are doing, besides reflecting sunlight and hiding the surface like a guilty secret. Venus has a cycle that imitates Earth in a way that feels almost cruel. There are clouds, there is something like rain, there is rising and falling, condensation and evaporation. It performs the motions of weather you recognize, but the substance is wrong. It is not water. It is sulfuric acid droplets suspended in layers. And when those droplets fall, they often do not reach the ground. They descend into warmer air, and they evaporate and vanish as if the planet changes its mind mid-sentence. So you get rain that forgets to arrive. If you have ever watched rain outside your window and felt comforted by the idea that it will soak into soil and feed plants, Venus removes that comfort with professional efficiency. The rain falls through a sky that cannot support it for long. It becomes vapor again. It returns to the clouds, a little loop of chemistry repeating without purpose, because purpose is not part of the job description. And you, drifting in the middle of it, notice how silent it all feels. No patter on leaves, no gutters overflowing, just droplets forming and falling and unforming. You can think about why it never reaches the ground. The deeper layers are hotter, and the droplets meet that heat and break apart. The atmosphere near the surface is also dry in terms of water. Venus does not have an ocean to replenish a familiar water cycle. So the clouds are not a gentle sea in the sky. They are a chemical system, a factory line, tuned to sulfur and carbon and heat. The clouds also contain other compounds in trace amounts, tiny bits of chlorine and other reactive molecules, a complicated chemistry set floating above a planet-sized oven. Some people like to speculate about life in those clouds. Not on the surface, obviously, not in the furnace and the crush, but up higher, where temperatures are more moderate, where pressure is closer to what you know. It is an interesting thought, a little pocket of habitability in a world otherwise designed to end you. But then you remember the acid, you remember the dryness, you remember that sunlight here is harsh and unfiltered in dangerous ways, and you remember that Venus has a habit of taking anything hopeful and placing it gently into a shredder. Still, as an observer, you can allow the idea to float by, a thought bubble in a corrosive sky. Then it pops quietly, and you return to the weather that is actually there. One of the strangest comforts of Venus is that it is consistent. Its atmosphere is thick, and it holds heat with a stubborn grip. So the planet does not swing wildly between day and night temperatures like the moon. It does not have sharp cold snaps. It does not have frosts that come and go. It is just hot, all the time, everywhere, near the ground, a constant condition, a monotonous disaster, and that steadiness affects how you imagine the air moving. On Earth, weather often comes from contrasts. Warm air rises, cold air sinks, and the planet's spin twists it into storms. On Venus, the contrasts are different. The atmosphere is so thick, the heat so well mixed, that the system behaves in its own slow rhythm. You can picture the planet as a sealed room that has been warming for a very long time. The air circulates, it finds patterns, it forms layers, and above it all, the cloud tops still race around like a sheet being snapped in the wind. Speaking of those racing clouds, they do more than move. They also hide the surface so thoroughly that ordinary light is almost useless. If you were hovering in orbit and you pointed a camera down, you would see only brightness and texture, no continents, no oceans, no mountain chains, just the same pale blanket, day after day. So, if you want to know what the ground looks like, you have to cheat. You have to use a kind of sight that does not care about clouds. But before we trade eyes for radio waves, it helps to picture the surface as it waits under all that weight, because beneath the false rain, beneath the rushing ceiling of clouds, Venus has its own slow geology, wide plains of lava, old flows frozen into stone, and volcanoes that may still be breathing in their sleep. And as you let that image form, the bright cloud world above begins to feel less like weather and more like a lid. A heavy lid, keeping the heat in, keeping the secrets hidden, while the surface below stays dark, dry, and patient, waiting to be noticed. Down there, under the lid, the ground is not sparkling or poetic. It is stone that has been cooked until the idea of cool feels fictional. It is a landscape with the color palette of old pennies and burned bricks. And if you could step onto it, the first sensation would be weight everywhere, not just the sky pressing down, but the air pressing into you. Any empty space becomes a target for collapse. Any weak seal becomes a confession. Congratulations, your lungs would learn why fish do not do mountain climbing, but you are not breathing it. You are only hovering, patient and untouchable, like a thought experiment. So you get to notice the shapes and the slow logic of a world without water. On Earth, water is a sculptor that never clocks out. It sneaks into cracks, freezes, expands, and breaks rock apart. It runs downhill, carrying grit like sandpaper in motion. It makes rivers, then valleys, then deltas, then whole coastlines. Venus does not have that kind of busy, liquid vandalism. No rain that reaches the soil, no streams that argue with gravity, so the surface keeps its scars differently. Less carving, more coating. Less delicate erosion, more blunt resurfacing. You can imagine it like a kitchen tray left in an oven for too long. Grease baked into the metal, stains layered on stains. Not pretty, but honest about the heat it endured. Venus looks like that. Broad, flattened plains with old flows set hard. Most of what we think we know down here points to volcanism, not a few polite mountains spaced out for postcards. More like a planet that once tried to repaint itself using lava, over and over, until the brushstrokes merged into wide plains. On Venus, lava does not have to compete with oceans. It does not have to meet water and explode into steam. It spreads, it cools, it thickens, it becomes another layer, and then it sits there, sealed under hot air, like a secret under glass. There are volcanoes too, and they come in strange styles. Some are tall shields, broad and low, like spilled batter that hardened. Some are domes, steeper, shaped by thicker lava that barely flowed. Some features look like pancakes, flat, round domes with raised rims. Yes, pancakes, a planet-sized furnace, and the geology still finds a way to be comedic. The term is pancake dome, and it means viscous lava oozed slowly. It piled up instead of running away, like it forgot where downhill was. You picture the lava as sluggish, heavy, unwilling to hurry, because basalt on Earth can flow like a glowing river. But if lava is richer in silica, it gets sticky and slow. It becomes the kind of material that builds domes and plugs vents. And when a vent plugs, pressure finds other hobbies. Sometimes it shatters the plug violently. Sometimes it leaks around the edges for years. On Venus, the details are hidden, but the shapes hint at the story. There are also fractures, long, wandering cracks across the plains. Some are rifts, places where the crust stretched and thinned. They are not cute little faults you step over on a hike. They are continent-scale wounds, traced by lines of volcanic activity. And then you notice the absence of something Earth cannot stop making. You do not see clear evidence of plate tectonics like home. No neat conveyor belts of crust diving under other crust. No global jigsaw puzzle of moving plates, grinding and recycling. Earth runs on plate tectonics the way a body runs on circulation. Heat rises, rock deforms, plates drift, continents rearrange. It is messy, but it is a system with outlets. Venus seems to hold its heat differently, like a sealed pot. One idea is that Venus has a stagnant lid. The crust acts like one big plate, not many. Heat builds underneath, slowly, until it forces its way out, not as constant motion, but as episodes of resurfacing. You can think of it as patience, followed by a tantrum. For a long time, not much changes at the surface. Then the interior insists, and vast areas get flooded with lava. Then quiet again, while the heat starts saving up. If that is true, Venus has long stretches of boring sameness, which is somehow worse than daily disasters, because at least daily disasters give you variety. Venus offers monotony until it doesn't. There is a lingering question here, soft and sharp at once. Is Venus volcanically active now? Is something still venting gas, still leaking heat, still rewriting small regions? Or is it mostly resting, like a tired engine, after a hard life? You cannot watch lava flow through the clouds with your eyes, but you can look for hints, chemical whispers in the air. For example, sulfur dioxide, a volcanic gas that sunlight breaks down. If it shows up in changing amounts, something might be replenishing it. Scientists have watched Venus for signs like that. Sometimes they see changes that look like volcanic breathing. Sometimes the data is stubborn and ambiguous, like Venus enjoying mystery. The planet rarely gives you a clean answer. There is also heat itself, the subtle glow of infrared radiation. Certain wavelengths can slip through small windows in the atmosphere. In those windows, you might catch warmer spots, like fresh lava cooling. Not a clear flame, more like a slightly brighter bruise on the map. And there have been observations that look like that. A few regions have shown odd thermal signatures over time. Not proof exactly, but the kind of clue that keeps you awake, which is ironic because you are listening to this in bed. Venus also has impact craters scattered across its surface. Not as many as the Moon, which is basically a punching bag, but enough to tell a story about age. Crater counting is a strange kind of clock. On an airless world, craters pile up for billions of years. On a geologically active world, craters get erased. So the number of craters on Venus suggests a surface that is not ancient, not young like a fresh lava field yesterday, but not primordial either. Many estimates point to a surface average age of a few 100 million years, which is old to you and young to a planet. It suggests something happened, maybe widespread resurfacing, a planet-wide reset, followed by a long, simmering quiet. And all of this is happening under a sky that never clears. No blue day to show you mountains in the distance. No horizon line that feels honest. Just that heavy orange light, absorbed and scattered by thick air. If you could stand there, your sense of distance would be wrong. Dense atmosphere reduces contrast, softens edges, hides far things. It would feel like being in fog that never lifts, a permanent heated haze baked into the world. Your footsteps, if you could make them, would sound strange. The dense air would carry low frequencies well. It would feel like sound had weight, like it sank instead of floating. And the ground under you would be hard but not comforting, because the rocks are not cooled by rain, not washed clean. Chemistry happens in the heat, slowly, relentlessly. Certain minerals could react with the atmosphere. The surface might be coated in altered compounds, like a stain that never dries. And there is another small cruelty. Wind still matters here. Even mild winds can push with real force, because the air is thick, so dust and grit can still travel, still sandblast gently over time. Not a raging storm, more like endless, slow abrasion. So the Venus surface changes, but at a different tempo. Not the lively churn of seasons and rivers, more like a long-term pressure cooker with occasional outbursts. Geology as a slow, stubborn argument with trapped heat. You might wonder what you would even see if a volcano erupted here. Not the bright red fountains you picture on Earth. The atmosphere would swallow contrast, muffle brilliance, and the light would already be dim and orange. But lava is still lava, and heat is still heat. Fresh flows could glow in wavelengths your eyes cannot see. Gases could rise, adding to the chemistry of the clouds above, and the surface would quietly keep score, layer after layer. The strangest part is how familiar the ingredients are. Rock, heat, gravity, gas, the same set of tools that made home. And yet, the outcome is this: an oven world behind a curtain. That is one of Venus's favorite lessons. Similarity is not safety. Being Earth-sized does not mean being Earth-like. It means the same physics can build a paradise or a pressure cooker. And if you are tempted to blame Venus for being evil, don't. Venus is not cruel. It is not angry. It is just efficient, like a machine doing what machines do. The planet does not hate you. It does not know you exist. If you tried to stand here, it would not punish you personally. It would simply apply the rules all at once. Which brings you to an awkward problem. You want to understand this surface, these planes and domes and fractures. But the clouds do not let you look. Light bounces off them and your camera sees only brightness. So you do what humans always do when nature blocks the door. You knock with a different tool. You stop relying on eyes and you start relying on echoes. You trade sight for something colder and more patient. Radio waves, long invisible ripples that do not care about clouds. They pass through the acid haze like gossip through a crowded room. And when they hit the ground, some of that energy comes back. This is where the story becomes oddly intimate, because to map Venus, you do not look at it. You touch it from orbit with electromagnetic fingertips. You send a pulse, then wait for the reply. Radar is basically that. You transmit radio waves toward a surface, the waves reflect, scatter, and return, and you measure the time delay and the strength of the echo. Time tells you distance. A stronger echo can mean a smoother surface or certain materials. A weaker echo can mean roughness or slopes scattering the signal away. It is not a photograph, more like a relief map built from soundless taps. You are listening for the shape of a world in the dark, like walking through an unfamiliar room with your hands out, except your hands are a spacecraft antenna, and the room is a planet, and the darkness is a cloud deck that refuses to cooperate. When radar sweeps across Venus, it builds strips of data, line by line, pass by pass. It stitches them into a global picture. It is slow, methodical work, like knitting a blanket from static, and eventually, the hidden surface becomes legible. The famous maps came from missions like Magellan in the 1990s. Magellan orbited Venus and used synthetic aperture radar. That phrase sounds like a corporate meeting, so here is the human version. You fake a huge antenna by moving and combining signals over time. As the spacecraft travels, it collects radar echoes from slightly different angles. With careful processing, you get much sharper detail. It is like taking many blurry photos and using math to sharpen them. Forget what you learned in school. That is the fairy tale. Here is the math. The result is a map where bright areas often mean rough, reflective terrain. Dark areas can mean smoother plains or angles that scatter the signal away. Mountains show up as textures, not colors. Craters appear as circles with rims and ejecta patterns. And suddenly, Venus has features you can name. Maxwell Montes, a highland region, towering compared to its surroundings. Aphrodite Terra, a vast area of complex terrain. Ishtar Terra, another continent-like highland. You call them continents, but they are not Earth continents. No oceans lapping at their edges, no rain-fed forests creeping up their slopes. Just high rock under heavy air, like islands in a sea of pressure. Radar also reveals tesserae, regions of highly deformed terrain. They look like tiled patterns, ridges intersecting at angles. The word tessera comes from little tiles and mosaics. On Venus, it is a mosaic made of crushed crust. Tesserae might be older than the lava plains. They might be remnants of a different geological era, a time when Venus's surface was being bent and folded intensely. a time before the possible resurfacing smoothed so much away. You are looking at the wrinkles of an earlier face, a face Venus hid, then partly replaced, and the only way you know it exists is because radar told you, because light never got the chance. There is something almost comforting about that. Venus will not show you its surface willingly, so you use a method that does not require permission. You send signals, and you take the echoes, and you build a picture anyway. But radar has its own quirks. It can be fooled by slope, by roughness, by material properties. A bright patch might be steep terrain facing the radar, or it might be something unusual in the rock. And Venus does have some unusual bright areas at high elevations. Some mountain tops reflect radar strongly. There are hypotheses, metallic frost deposits, like lead sulfide or similar compounds. Not snow you would touch, but chemistry condensing where it is slightly cooler. Imagine that, a mountaintop on Venus, coated in something like a metal dew. Not white and soft, but reflective and strange. A parody of alpine snowfields made of minerals and heat. You could call it weather, in a broad sense. Not wind and water, but condensation and deposition. A cycle of vapor and surface coating, driven by temperature and chemistry. Even here, the planet finds a way to have seasons without relief. Radar mapping also lets you measure elevation with altimetry. You send a pulse straight down, measure return time, infer height. Piece by piece, you build a topographic model, a ghostly globe of highs and lows drawn in data. And the elevations matter because pressure and temperature shift with height. Even on Venus, climb higher and it cools. Not to pleasant, necessarily, but to less murderous. Highlands may be slightly kinder, in the way a lesser burn is kinder. And those differences affect chemistry. What condenses where, what reacts faster, what gases linger. So the map is not just geography. It is a guide to how the atmosphere and surface talk to each other. Now, while you are up here in orbit, reading radar like Braille, you might notice how human this process feels. We are pattern hunters. We take a world that refuses to be seen, and we invent a way to see it. It is a kind of tenderness, disguised as engineering. A spacecraft circles a planet, alone, endlessly, sending pulses downward, waiting for echoes, building a portrait out of returns and delays. And yet, it is also cynical practicality. We cannot send explorers to stroll here, so we send machines that do not care about heat the way flesh does, and even they die quickly on the surface. Orbiters last longer because distance is mercy. Up here, above the worst pressure and heat, hardware can survive. It can keep listening. It can keep mapping. So you hover with it, and you let the radar picture sharpen. You see plains that look smooth, likely basaltic lava fields. You see ridges, fractures, coronas, and domes. Coronas are large circular features, possibly from rising plumes of hot material. A corona is not a halo of light, not here. It is a ringed scar, sometimes with concentric fractures, a sign that the mantle may have pushed upward, then sagged back down. The crust responding like skin over a slow boil. You begin to appreciate how Venus might vent heat without plates, plumes rise, the surface bulges, cracks form, lava erupts. Then the system relaxes. A long, slow-breathing cycle, measured in geological time. And speaking of time, the clouds above are not just hiding the surface, they are also telling you about Venus's history. Because an atmosphere like this does not appear by accident. It is the residue of choices made by physics long ago. So you let the radar map sit in your mind like a quiet, grayscale dream. You accept that this is the only way you get to see the ground. And then, naturally, your thoughts drift to the question humans cannot resist. How did this happen? How does a planet so similar in size to Earth become so different in outcome? How do you end up with oceans and forests on one world and a CO2 furnace with acid clouds on the other? It is the same sun, roughly the same neighborhood, almost the same mass, and yet one is a soft place to sleep. The other is a cautionary tale wrapped in a bright disguise. The simplest answer is that Venus is closer to the sun. It receives more sunlight, more energy, more insistence. But distance alone is not the whole story, because small differences can snowball into total transformation. You know this from ordinary life. One missed email becomes a week of chaos. One tiny crack in a dam becomes a flood. One little change in an atmosphere becomes a runaway greenhouse. Runaway greenhouse is the phrase that matters. It sounds dramatic, like a movie trailer, but the process is slow enough to be boring. It is feedback, nature's favorite way to ruin your plans. Here is the gentle loop. A planet warms a little. Warmer air holds more water vapor. Water vapor is itself a greenhouse gas. So more water vapor means more heat trapped. More trapped heat means warmer temperatures. Warmer temperatures mean even more water vapor. The loop closes, then tightens. On Earth, this feedback exists, but it is moderated. We have oceans, clouds that reflect sunlight, weathering that removes CO2. We have a carbon cycle that, over long times, acts like a thermostat. Not perfect, but functional enough to keep liquid water around. On Venus, something pushed the system too far. Maybe early Venus had oceans, at least for a time. There are models suggesting it could have been temperate long ago. But if it warmed enough, the oceans would evaporate. An evaporated ocean means the sky becomes thick with water vapor. That traps more heat, accelerating the warming. Eventually, the upper atmosphere gets flooded with water molecules. And then, sunlight does what sunlight does. Ultraviolet light breaks water apart. It splits H2O into hydrogen and oxygen. The lightweight hydrogen escapes to space more easily. The oxygen can react with rocks or be lost by other processes. Over time, you can dry out a world. You can take an ocean, turn it into vapor, then turn the vapor into lost hydrogen and leave behind a planet that cannot easily make water again. So Venus may have lost its water early, or gradually, or in episodes. And without water, you lose a major way to store carbon. On Earth, Colorado too dissolves in oceans, becomes carbonates, gets locked into rock. Water is not just comfort, it is chemistry infrastructure. Without that infrastructure, volcanic CO2 accumulates. Each eruption adds gas to an atmosphere that cannot easily remove it. And once CO2 is abundant, it traps heat efficiently. Then the surface heats, and the cycle leans into itself. You can picture Venus as a planet that missed one crucial exit ramp: a little more sunlight, a little less initial water, a different early rotation, different impacts, and the system tips into a stable hell. Stable meaning it stays that way. Not stable meaning safe. There is also the matter of magnetic fields. Earth has a global magnetic field that deflects much of the solar wind. Venus does not have the same kind of strong intrinsic field today. That could affect atmospheric loss, especially of lighter molecules. But again, it is not one single cause. It is a pile of influences stacked like those invisible blankets. Distance, water, carbon cycling, geology, solar radiation. Enough small pushes, and the planet slides into a different basin of fate. And the unsettling part is how ordinary the physics is. Nothing supernatural, no cosmic punishment, just molecules absorbing infrared light, just feedback loops doing what feedback loops do. That is why Venus is a favorite in climate discussions, not because Earth is about to become Venus next week, but because Venus shows what a greenhouse can do when it runs unchecked. It shows the upper limit of warming, written in rock and cloud. And while you are thinking about that, you might remember the brightness again. Venus reflects a lot of sunlight because of its clouds. Those clouds cool the planet's upper atmosphere by reflecting. But below, the CO2 traps heat so effectively that it does not matter. It is a layered contradiction, bright and reflective, yet scorching at the surface, like a person smiling while actively ruining your day. The planet looks gentle from afar and lethal up close. And maybe that is the real lesson. You cannot judge habitability by appearance. A bright star can sterilize worlds. A cloudy planet can hide an oven. A familiar size can still mean an alien outcome. Now, keep that thought suspended for a moment, because there is another oddity about Venus that connects everything. Its rotation is slow, and it is backwards compared to most planets. Retrograde rotation, a fancy term for spinning the wrong way. It is as if Venus decided to drive against traffic. Some theories suggest massive impacts early on could have altered spin. Others suggest atmospheric tides over time could have torqued the planet. In any case, the slow spin affects weather patterns and circulation. A slowly rotating planet has a different balance of forces. On Earth, the Coriolis effect helps shape storms and trade winds. On Venus, the weak Coriolis effect near the surface changes how air moves. And yet, the upper atmosphere still superrotates. That superrotation remains partly mysterious. It likely involves solar heating, waves in the atmosphere, and momentum transported downward and upward between layers, like a complex machine made of gas, running continuously. So Venus becomes a laboratory for atmospheric physics, not because it is pleasant, but because it is extreme and persistent, a place where you can test models of circulation under dense conditions, a reminder that wind is not just a breeze through trees. And speaking of dense atmospheres, Venus also has a strange relationship with electricity. There are hints of lightning, but it is debated and complicated. Some missions detected signals that could be lightning-like, but the thick clouds and chemistry make it hard to interpret. On Earth, lightning comes easily with water clouds and ice collisions. On Venus, with sulfuric acid and different dynamics, it is less straightforward. The planet keeps its electrical secrets, like it keeps its surface secrets. The more you learn, the more the theme repeats. Venus is not loud about its weirdness. It is quiet, thick, and consistent. It forces you to infer, to reconstruct, to guess carefully. And this is where you start to feel the contrast with Earth. Earth is a talkative planet. It shows you oceans, continents, clouds you can see through. It gives you windows, literal clear skies, into its workings. Venus gives you a curtain and tells you to figure it out anyway. So you do, with radar and spectroscopy and stubbornness. You look at how sunlight interacts with the atmosphere. You measure gases by how they absorb specific wavelengths. You track temperature profiles by radio occultation. That is when a spacecraft signal passes through the atmosphere to Earth. The signal bends, and the bending tells you density changes. Again, you are mapping a world by how it distorts a wave. It is all indirect, all careful, a whole science of listening to what you cannot see. And maybe that is why Venus feels like a bedtime planet, because it is always half hidden, like a dream you never fully recall. But there is something else, deeper and older in the comparison. Earth and Venus, likely formed from similar starting materials, rocky planets in the inner solar system, share many ingredients: silicates, iron, volatiles like water and carbon compounds. So the divergence is not about alien chemistry. It is about history, timing, initial conditions, the long consequences of small differences. If Venus lost its water, it lost its cooling pathways too. Water helps move heat around, helps lubricate tectonics, helps weather rock. Without it, the surface becomes less able to recycle carbon. So the atmosphere thickens and the furnace stabilizes. Earth, meanwhile, kept its oceans. It developed a working carbon cycle with rocks and life. Photosynthesis pulled CO2 down and released oxygen. Plate tectonics buried carbonates and vented gases in balance. Balance is not peace. It is just a dynamic struggle that happens to keep temperatures survivable. Earth is not gentle. It is merely not Venus. A low bar, but you take what you can get. And while you are drifting with these thoughts, you begin to see Venus less as a villain and more as a sibling. Not an evil twin, just a twin who made different choices at the molecular level. A sibling who moved closer to the sun and never recovered. Which is why Venus is so valuable scientifically. It is a controlled comparison you can never build in a lab. Two rocky worlds, similar size, different climate outcomes. A natural experiment that has been running for billions of years. Now, even with all this, you still might want something simple and human to hold on to, a single image that ties the science to sensation. So imagine, for a moment, pouring a glass of carbonated water. The bubbles rise, pop, vanish. That is CO2 leaving solution, escaping into air. Now imagine the opposite. CO2 filling an entire sky, pressing down. A whole atmosphere of the stuff that makes your drink fizzy. The molecule is not exotic. Your body makes it constantly. Plans consume it. But scale changes everything. A familiar ingredient can become an overwhelming environment. And this is where the mind does a quiet pivot. Because Venus is not just a planet with weird weather. It is a warning about scale, about accumulation, about feedback. It is what happens when a system has no easy release valve, but you are not trapped in that system. You are just visiting it with your imagination and my tired voice. You are allowed to hold the lesson lightly, like a stone in your palm, and then let it sink back into the dark, because there is still more to understand about how we know what we know. Venus is hidden, so our knowledge is stitched from indirect methods: radar maps, chemical spectra, pressure and temperature profiles, short-lived landers that died quickly, but spoke while they could. Those Soviet landers, the Venera missions, they dropped through the clouds like doomed messages in bottles. They carried cameras, drills, sensors, and they transmitted data back before the heat took them. Their images show rocks that look fractured and worn. Some rocks appear layered, some angular. The horizon is close, the lighting dim and strange. It is a world that feels indoors, despite being outside. Those landers also measured the chemistry at the surface. They confirmed the crushing pressure and the heat. They sampled the atmosphere, mostly CO2, with nitrogen as a minor component. They detected traces of other gases too, like sulfur compounds. All of it fits the picture you have been building: a thick greenhouse, a dry surface, a chemical cloud deck, a planet where weather is less about water and more about circulation and acid. A planet that runs hot and stays hot. And you can keep turning the comparison screw. On Earth, water vapor is important, but it condenses and rains out. On Venus, sulfuric acid condenses and falls, then evaporates before landing. A cycle without ground contact. Weather that never completes its own gesture, which means the surface is isolated in a way Earth's surface is not. Earth's surface and atmosphere exchange constantly through water. On Venus, the exchange is more limited, more chemical, more slow. The planet is like a sealed container with internal stirring. There is a word you might hear in discussions of Venus: habitability. The ability of a place to support life as we know it. Surface Venus is not habitable for Earth life, not even close. But the cloud layers at certain altitudes have temperatures and pressures that are more Earth-like. That is the narrow zone where some people speculate about microbes. If life could tolerate acid, dryness, and intense radiation, it is a big if. But it is also a useful prompt, because it makes you think about what life needs and what it can endure, and it forces you to separate comfortable from possible. Life on Earth includes extremophiles, organisms living in hot springs, in acid pools, in deep rock pores. They do not thrive because the world is kind. They thrive because chemistry allows a small foothold. So when people imagine Venus cloud life, they imagine droplets as tiny habitats, floating and cycling. They imagine microbes protected inside aerosols, feeding on chemical gradients, suspended in perpetual motion. And then reality taps you on the shoulder. Sulfuric acid is not a mild inconvenience. Water activity is low, meaning there is little free water for biochemistry. Ultraviolet radiation is harsh in the upper layers, so the idea remains speculative, unresolved, interesting, but not a bedtime certainty. Venus keeps its secrets. As usual, still, The speculation led to careful measurements. People looked for unusual gases that might hint at biology. They talked about phosphine for a while, a claimed detection that became controversial and heavily debated. That story is not finished, and that is the point. Science is often a slow argument with noise. A signal appears, then disappears. Weaker teams disagree, methods improve, conclusions shift. Venus is a good planet for that, because it is hard to observe, so uncertainty is always in the room. It teaches patience and skepticism. It teaches you to love the phrase, "We do not know yet." Now, while all this happens, the planet itself keeps running its simple routines. Clouds circulate. Acid condenses and evaporates. Winds race at the top while the ground remains lethargic. And beneath it all, the surface may still be changing slowly. A lava flow here, a vent there, a chemical reaction coating rocks, a crater slowly softened by time and atmosphere, not erased by water, but aged by heat and pressure. You could spend a lifetime studying Venus and still feel like an outsider, because you cannot walk there. You cannot stand under a Venus sky and feel the wind. You cannot smell the air and tell yourself it is real. But you can map it. You can measure it. You can infer its past by its present. And you can use it as a mirror for Earth's delicate balances, which returns you, softly, to that tale of two neighbors. Two planets that likely started with similar building blocks. Two planets that ended up with radically different climates. And the split matters because it teaches humility. It also teaches appreciation, though not in a sentimental way. More in a practical, almost annoyed way, like realizing your boring old plumbing is actually a miracle. Like realizing breathable air is not the default setting, because if you zoom out far enough, Venus is the common outcome, not Earth. Not literally, but conceptually. A planet that loses water, accumulates greenhouse gases, and becomes inhospitable. Earth is the weird one, the one with stable oceans for billions of years, the one with plate tectonics that recycle carbon, the one with a biosphere that hacked the atmosphere. And there is something worse if you keep following the thread, because Venus is only one kind of weird weather. There are worlds where it rains glass, worlds where winds carry iron vapor, worlds where storms last for centuries. But we are not leaving yet. Not really. For now, you are still close enough to Venus to feel its brightness, still close enough to watch the cloud tops slide by like slow silk. So, you keep thinking about how early Venus might have felt. If it did have oceans, the sky would have been different. Clouds of water, not acid. Rain that actually reached the ground. Shocking, I know. Those oceans would have moderated temperature. They would have stored CO2. They would have fed a rock weathering cycle. They might have kept the planet stable for a long time. And then, gradually, the sun brightened. Stars like ours increase luminosity over time. A slow, steady brightening over billions of years. Not a sudden flare, just a creeping increase. So early Venus could have crossed a threshold. A point where evaporation outpaced condensation, where water vapor filled the atmosphere, where the runaway began. Once the oceans are gone, the game changes. The surface dries. Tectonics may slow or change style. Carbon accumulates in air, not rock. the greenhouse stabilizes at a high temperature. At that point, Venus becomes very hard to rescue. Not that it needs rescuing, but if you are the kind of creature that wants water and oxygen, you stop calling it almost Earth, and you start calling it Nevermind. And that is why, when you see Venus as an evening star, bright and steady near the horizon, you are looking at a planet that might once have been different. A world that took a path and stayed on it. The light you see is reflected cloud light, a bright disguise, a reminder that appearances are cheap in the solar system, and reality is expensive. Now, with all this in mind, you remain in orbit a little longer because there is still something soothing about methodical mapping. The spacecraft circles, the radar pulses, the echoes return. A strip of data becomes a mosaic becomes a globe becomes a story, and the story becomes a quiet understanding you can carry. You begin to notice, too, that the clouds are not uniform. There are subtle features in ultraviolet images, dark streaks that absorb ultraviolet light more strongly, some unknown absorber still debated painting patterns in the sky. It might be sulfur compounds, or chlorine, or something more complex. It might be particles with specific optical properties. The details matter to atmospheric chemistry, but the overall impression is simple. Even the clouds have secrets inside the clouds. Even the veil has a veil. Venus is a nested set of mysteries, each one thick and patient. And you, drifting beside it, keep collecting what you can, because that is what you do. You observe, you infer, you build models, then break them, then rebuild them. You accept that certainty is rare and progress is slow. And while you are doing that, the planet continues to super-rotate above a slow spinning surface, a rushing ceiling over a drowsy floor. Whether as choreography, indifferent to your curiosity, it is almost enough to make you think Venus is alive, not biologically, but dynamically, like a system with habits, a machine that has found a stable rhythm and refuses to change. Speaking of stable rhythms, there is one more rhythm Venus forces you to confront: day and night. On Earth, day and night feel like punctuation, a daily reset, a cooling period, a chance for weather to shift. On Venus, the day is extremely long, but the surface does not cool much anyway because the atmosphere hoards heat. So the difference between dayside and nightside temperatures is small. The greenhouse and thick air distribute heat around, which means the usual driver of daily weather is muted. Another reason storms are not like Earth's. The weather here is not a daily drama. It is a steady state with moving parts, a slow circulatory system, transporting heat and chemicals. A planet that does not do surprises, it does persistence. And persistence is the theme you keep bumping into. Persistent clouds, persistent heat, persistent winds aloft. The kind of persistence that would be unbearable if you lived here. But as a listener, safe where you are, you can let it be hypnotic. A world that repeats itself with minor variations, like ocean waves. Still, there is a final piece you will want before you drift onward. Because when you compare Venus and Earth, it is tempting to treat Venus as Earth's future. But Earth is not automatically headed there. Earth has oceans, a different distance, different history, active plate tectonics. Earth has a biosphere that modifies the atmosphere. These differences matter. Venus is not a prophecy. It is a boundary condition, a demonstration of how far greenhouse physics can go, a reminder that climate is a system, not a mood, and the system responds to inputs, feedbacks, and time. Time is the part humans always underestimate. We think in years, decades, maybe centuries, if we are feeling ambitious. Planets think in millions of years, and they do not rush. Venus took its time becoming this, and now it will take its time staying this way. A bright, hot lesson, hanging near the sun, a pearl behind acid curtains. You keep orbiting, and the radar map in your mind grows more complete. You can almost feel the hidden mountains, the lava plains, the fracture zones. You can almost imagine standing on a tessera ridge, looking out into orange haze that never clears. Almost. But you do not need to go there to learn from it. That is the quiet luxury of distance. Observation without suffering. Knowledge without the pressure crushing your suit into a sculpture. And as you let Venus remain what it is, you begin to notice how the mind naturally seeks contrast. Because the easiest way to appreciate a calm room is to remember a place where the air itself tries to end you. So your thoughts start to pivot, gently, toward home. Not leaving space yet, not closing the story, just letting Earth enter the frame as a comparison. A planet where clouds are mostly water and rain usually finishes the job. A planet where pressure is 1 atmosphere, not 90, where the night can cool the ground, where wind can be playful instead of oppressive, where weather can be inconvenient, not existential. And as that contrast settles in, you stay with Venus a little longer, watching the cloud tops swirl, watching sunlight gleam off acid droplets, and quietly holding the thought that 2 neighboring worlds can share a birth and still grow into completely different kinds of solitude. You keep circling, and you let the brightness do what it always does, hide the inconvenient parts, because if you stare at Venus long enough, your mind starts inventing oceans again. A pale globe, smooth and glowing, like it is wrapped in innocence. But innocence is just a lighting choice. So you do what you have been doing all night. You take the pretty surface of the story and you turn it over. You look for seams. You look for the way the world actually works when nobody is watching. And one seam is right there in the air itself. You are above the clouds now, in the thin, cold edge of atmosphere. Your spacecraft is quiet except for the soft insistence of systems. Below you, the cloud tops swirl, like cream stirred into coffee very slowly. And you remember that, on Venus, even the sky has a chemistry problem. Carbon dioxide is most of the atmosphere, yes, but it is nitrogen too, like Earth has, just less of it. And then there are the trace gases, little spices that change the whole flavor. Sulfur dioxide, carbon monoxide, water vapor in small amounts, and sulfuric acid suspended as droplets, making clouds that punish touch. Venus is a lesson in how a trace ingredient becomes an identity. On Earth, sulfur compounds are often local. Volcanoes, pollution, hot springs. On Venus, sulfur chemistry is not local. It is the weather itself, baked into the global routine. The basic loop is almost simple, which makes it more unsettling. Sulfur dioxide rises from lower layers, sometimes from volcanism. Sunlight hits it up high, and it reacts. turning into other compounds. Those compounds join water, what little water exists, and make sulfuric acid. Then, sulfuric acid condenses into droplets, and the droplets become clouds. You can picture a factory in the sky. Inputs come up. Sunlight runs the machinery. Droplets roll off the line, and then gravity pulls those droplets down. Slowly, patiently, they fall into warmer air, and they evaporate, breaking back apart. The pieces drift upward again, and the factory keeps working. It is a water cycle. In silhouette, a parody of Earth. Same choreography, different music, and the instruments are corrosive. And speaking of corrosive, your mind always asks the same question. If the clouds are sulfuric acid, why are they still there? Why do they not simply eat the planet and be done with it? The answer is boring, which is the Venus way. Sulfuric acid is aggressive, yes, but it needs water to stay acid. And Venus is not generous with water. The droplets are concentrated, and the lower atmosphere is dry. At the surface, the chemistry changes, and different minerals can form. It is a balance of reactions, not a dramatic dissolution. Also, the acid is mostly up high, where it is cooler. Closer to the ground, the air is too hot for those droplets to persist. So the worst of the acid floats above, like a ceiling stain. The surface gets other kinds of chemical weathering. Slow, hot, suffocating. Not sizzling splashes, more like long-term damage. Now, you might think of clouds as soft things. On Earth, you can fly through them, and the plane just gets damp. On Venus, you fly through, and your instruments start writing their wills. The cloud deck has layers. An upper cloud layer, a middle one, a lower one, and between them, haze. Fine particles that catch light and scatter it. Visibility drops, not suddenly, but like a dimmer switch turns slowly down. The sun becomes a pale coin behind cloth, and if you were inside it, you would not feel the romance of fog. You would feel your equipment aging in real time. Still, you are not inside it. You are above, and you can afford curiosity without consequences. So you watch the patterns, and you notice another strange detail. The winds that whip around the planet do not just move clouds, they move heat and chemistry, distributing this acidic weather worldwide. This is why Venus is so consistent. It is not that the planet is calm, it is that the planet is well mixed. The thick atmosphere and the strong circulation smear out differences. So day side and night side do not diverge much at the surface. It is all the same oven everywhere, all the time. That consistency is soothing to study in a grim way. No sudden cold fronts, no seasonal surprises, just stable extremes, like a machine that found one setting and snapped off the dial. You let that thought hang, then you let it drift. Because there is something else about Venus that keeps people awake, not because it is dramatic, but because it is unresolved. Lightning. On Earth, lightning is a familiar violence. Charge separates in clouds, often with ice, collisions, and turbulence. A spark forms, then a channel, then the sky tears open in light. We are used to it, which is hilarious, given what it actually is. On Venus, the question becomes awkward. Can you get lightning in sulfuric acid clouds? Can charge separate the same way? without the same water-ice processes? And if lightning exists, how often does it happen and where? There have been hints, signals that sound like lightning radio bursts. Some spacecraft have detected electromagnetic noise consistent with sparks, but hints are not the same as certainty, and Venus likes ambiguity. The thick atmosphere complicates detection. The spacecraft environment can create its own noise, and the planet's ionosphere can warp signals in ways that mimic lightning. So, the honest answer, the scientific bedtime answer, is this: lightning on Venus is possible, maybe even likely sometimes, but it is not confirmed in the clean, satisfying way you would want. You get maybes and arguments and papers responding to papers, and Venus continues swirling, uninterested in your desire for closure. There is a darker irony here. If lightning exists, it could affect atmospheric chemistry. It could help make certain compounds break others apart. Tiny electrical events influencing the global cloud factory. So the question is not just spectacle. It matters to the chemistry that makes Venus look so bright. And brightness brings you back to the thing you saw in ultraviolet. Those dark streaks and patches in the clouds, absorbing ultraviolet light. Something is there, some unknown absorber, still debated. It could be sulfur allotropes, chlorine compounds, iron salts. It could be complex aerosols that form under specific conditions. Some people predictably whispered about life, because whenever we see an unknown, we try to move in emotionally. But unknown does not mean alive. Most unknowns are just chemistry we have not pinned down yet. A universe full of processes that do not need you as a protagonist. Still, you cannot blame the imagination. If the upper clouds have Earth-like pressure and temperature, for a band of altitude, it is tempting to picture microbial floaters riding the winds, aerosols as tiny lifeboats, chemical gradients as food, and Venus, for once, looking almost hospitable. If you ignore the acid, then you remember water activity again. Life, as we know it, needs accessible water. Sulfuric acid droplets are not friendly water. They bind it, they change it, they reduce what biology can use. So the cloud life idea is a fragile hope in a harsh place. But hope is a useful tool for science. When it stays disciplined, it motivates missions, it motivates measurements, it motivates better instruments and better models. Even if the final answer is boring chemistry, the path is instructive. And speaking of instruments, your orbiting viewpoint is comfortable, but limited. You can map terrain with radar, yes. You can measure gases with spectroscopy, yes. But weather is not only composition. Weather is motion and layers and temperature changes with height. So you start thinking about what it took to actually sample Venus's air. Long before you were drifting here in this sleepy story, humans sent probes that did not plan to return. They did not need to return. They just needed to fall and report. The Soviet Union built a whole lineage of Venus missions. Venera, a name that sounds delicate until you realize what it endured. Some were flybys, some were landers, some were atmospheric probes. Each mission was a timed conversation with a planet that kills hardware. To survive, even briefly, They used pressure vessels and insulation, thick shells like deep-sea submersibles, but for air instead of water. They used cooling systems and careful timing. And still, Venus won every time, eventually. But not before the probes measured what you are now imagining. Temperature rising as they descended, pressure climbing like a slow, steady threat, wind speeds changing with altitude, cloud layers, haze layers, chemical profiles through Venus's atmosphere. It feels like sinking, not in water, but in density. Your parachutes behave differently because the air is thicker. Descent can be slow, almost leisurely, despite the danger. A probe can spend a long time drifting down, taking data, transmitting upward. A calm fall into a furnace. That is a strange image if you let it settle. A machine hanging under a parachute in dim orange light, acid droplets streaking past like slow rain. Instruments ticking, recording, radio signals climbing back up through layers of gas into space. And somewhere far away, on Earth, someone listens. A faint stream of data telling you the weather on a world you cannot visit. It is intimate in a dry, technical way. A planet speaking through numbers and humans translating them into a story. Now, those numbers matter, but you do not need all of them. You only need the sensations they imply. Heat that never breaks. Pressure like deep water. Air so thick it behaves like liquid. Clouds made of acid, reflecting sunlight like polished bone. And once you have those sensations, your mind does something natural. It wants to compare, not just to Earth, but to other worlds. Because Venus is not the only planet with weather that feels like a joke. It is just the closest reminder, and it makes a good stepping stone, an entry into the wider catalog, a solar system where each planet runs its own version of physics. But you do not leave yet, not fully. First, you let your attention settle on one last Venus detail, something that seems small but changes the whole feel of the sky, the speed of sound. In thick, CO2-rich air, sound behaves differently. The speed depends on temperature and the properties of the gas. Venus is hot, which tends to make sound travel faster. But carbon dioxide has different molecular behavior than nitrogen-oxygen air. The result is that sound speed near the surface is not what your instincts expect. More importantly, sound carries differently. Dense air transmits pressure waves efficiently. Low rumbles would travel. A distant impact might sound close, because the haze hides distance visually. And if the wind moves slowly, it can still shove with heavy force, without loudness. So, a Venus landscape might feel eerily quiet visually, and yet acoustically heavy. You would not hear birds, obviously. You would not hear leaves or insects or rain on rooftops, but you might hear the low moan of wind around rocks, if anything survived long enough. A deep, slow sound, like air moving through a giant instrument. Congratulations! You have found a planet where silence is not empty, it is dense. That density also changes flight. On Venus, near the surface, the thick air provides buoyancy. A balloon could float if it can resist the chemistry. In fact, there have been balloon missions and serious proposals for more, because if you can stay in the temperate layer, You can avoid the surface horror. You can hover where pressure and temperature are manageable. Like a cruel compromise. It is one of the few places in the inner solar system where you could, in theory, float in air with almost Earth-like conditions, above an unlivable surface, beneath an acid cloud ceiling. A floating lab in a narrow band of relative mercy. That band has become a recurring idea. Not colonization, not fantasy cities, just science, platforms, drifting for weeks, measuring winds, chemistry, particles, sunlight, listening to a planet's atmosphere like a long, continuous sigh. And that brings you to a slow, sleepy realization. Venus is not a single environment. It is a stack. Cold upper air, acidic cloud layers, dense, hot lower atmosphere, and then the surface. A vertical world where altitude matters more than latitude, whether not as a horizontal map, but as a deep column. On Earth, you live at the bottom of the atmosphere and look up. On Venus, the bottom is punishment and the middle is temptation. It flips your intuition. It makes you think in layers and thresholds and narrow habitable bands. Now, speaking of layers and thresholds, your thoughts start drifting back to the big question of divergence. Why Earth did not do this, and Venus did. You already have the outline. Sunlight, water loss, carbon cycling failure, but you can make it more tangible, more like a story you can inhabit. So imagine you are early Venus, long ago. Not the Venus you see now, but a younger world. The sun is slightly dimmer than today, but still close and warm. Volcanoes vent gases, like they do on young planets. Water arrives by impacts and by chemistry inside rocks. If you have enough water, it pools. Oceans form, or at least seas. Clouds form, made of water, not acid. Rain reaches the ground, cooling the surface, feeding weathering. Carbon dioxide dissolves into the ocean, reacts with rock, becomes carbonates. A slow sink for greenhouse gas, a way to keep temperatures in check. And then, slowly, the planet warms. Not suddenly, not with a villain monologue. Just a little more sunlight, a little more greenhouse, a little more evaporation, more water vapor in the air, which traps more heat, which evaporates more water. At first, it might look like a humid world, thick clouds, heavy rain, warm oceans, a greenhouse, but a manageable one. Then you cross a line where the upper atmosphere stays wet, where water vapor reaches high altitudes in large amounts. Up there, sunlight is harsh, especially ultraviolet. It breaks water molecules apart. Hydrogen, being light, escapes more easily to space. You can imagine the planet exhaling its oceans, one atom at a time, a slow leak you cannot patch. As hydrogen leaves, the planet dries. Oceans shrink, then vanish. Weathering slows, because weathering needs water. The carbon sink collapses. Volcanoes keep venting carbon dioxide, and there is nowhere for it to go. So the atmosphere thickens, and thickening means more heat trapped. At some point, you are no longer in a humid world. You are in the beginning of the furnace, and once the furnace stabilizes, it is hard to reverse. Because to cool down, you would need to remove carbon dioxide or add reflectivity or somehow rebuild oceans to restart the carbon cycle. And the conditions that would allow oceans no longer exist. This is a one-way door in practical terms, not metaphysically, but physically. The system reaches a state that is stable, even if it is unpleasant. A stable attractor, a basin in climate space. Once you roll into it, climbing out is difficult. Earth has its own basins, its own thresholds, snowball Earth episodes, warm periods, ice ages, but Earth has a thermostat of sorts in the long carbon cycle. Weathering removes carbon dioxide faster when it is warm and wet. Volcanoes add it back over time. Life modifies it too, creating new pathways for carbon storage. Venus lost the wet part, so the thermostat broke and the planet settled into a different equilibrium. None of this makes Venus bad. It makes Venus a case study, a textbook example written in clouds and heat. And because it is so close, it is hard not to stare at it. Which is why modern missions keep coming back in plans and proposals. Orbiters to map again, with better radar. Landers designed to last longer, with high-temperature electronics. Balloons to float in the temperate layer. Spectrometers to sniff trace gases more precisely. There is even interest in seismology, which sounds funny on Venus. On Earth, you drop seismometers, and they listen to the planet's heartbeat. On Venus, dropping a delicate sensor onto a hot, crushing surface is ambitious. But people still think about it, because quakes would reveal interior structure. And interior structure tells you about heat flow and tectonics and volcanism. You can also do seismology from the air. In theory, pressure waves from quakes can travel upward. Balloons could detect infrasound, very low-frequency signals, the planet trembling, and the atmosphere carrying the rumor of it. That is the kind of idea humans love. A workaround, a clever method that turns a hostile environment into a measurement tool. And that is, quietly, one of the real stories here. Venus forces ingenuity. It forces indirect observation. It forces you to accept uncertainty, then reduce it slowly. Now, your mind has been on Venus for a long time. It has earned a gentle pivot, not a hard cut, not a dramatic leap, just a drift outward, because once you have stared at one planet's weather long enough, the solar system starts to feel like a shelf of different climates. And you are still a traveler, even if you are traveling with your eyes closed. So you let Venus shrink behind you, still bright, still hiding itself. You let it become what it often is from Earth, an evening star, a point of light that looks like comfort and means none. As you drift away, you keep a few Venus facts in your pocket. Not numbers, not charts, just textures. Acid clouds like a permanent lid, pressure like an ocean made of air, heat like an oven that never cools, winds aloft, racing over a sleeping surface. Those textures become your baseline for weird weather, a reference point, and now you start wondering, very naturally, what counts as weather elsewhere? Because on some worlds, the sky is not made of carbon dioxide at all. On some worlds, the clouds are ammonia or methane. On some worlds, the storms are so large they become geographic features. But for now, you are still in the inner solar system's mood. rocky planets, thin atmospheres, thick atmospheres, no atmospheres. And the next comparison comes almost by itself, like an intrusive thought. Mars. Mars is not a furnace. Mars is a freezer with dust problems. And compared to Venus, it feels almost delicate, a thin atmosphere, too weak to hold heat well, a world where night actually matters. If Venus is pressure and persistence, Mars is absence and exposure, and its weather is weird in the opposite direction. You approach Mars in your imagination, and the first sensation is not warmth. It is that the sky barely exists. A thin veil of carbon dioxide, not enough to press on you like a hand, not enough to keep you warm either. Mars air is thin enough that liquid water is unstable on the surface today, not because it cannot exist at all, but because it boils easily. Low pressure lowers the boiling point, and the planet does not give water a chance. So when you think of Mars weather, think of sublimation and frost, ice turning directly into gas, like it cannot be bothered with melting. Mars has seasons, though. Not mild ones, but real ones, because the planet's tilt is similar to Earth's, and the orbit is more elliptical, which makes some seasons more intense. So the poles grow and shrink caps, but not just water ice. Carbon dioxide itself freezes at the poles in winter. It forms dry ice frost and slabs, seasonal caps that come and go. So Mars has weather where the atmosphere partly collapses each winter. The air literally settles onto the ground as ice. You can picture it, winter night at the pole, darkness lasting months, temperature dropping so low that carbon dioxide condenses. The sky thins as the gas leaves it, turning into frost. Then spring returns. Sunlight warms the cap and it sublimates back, the planet inhaling and exhaling its own atmosphere. Congratulations! You have found a world where the air snows. And that matters for winds, because as pressure shifts with the seasons, air moves. You get strong winds, even in thin atmosphere, because gradients drive motion. And Mars has dust, fine, dry, electrostatic dust that loves to travel. So the iconic Mars weather is the dust storm, sometimes local, like a small spinning column called a dust devil, sometimes regional, spreading across continents, sometimes global, wrapping the whole planet in a tan haze. A global dust storm on Mars is not like a hurricane. There's not much water, not much latent heat release. The energy comes from sunlight heating dust and air, driving circulation. Dust lifts, absorbs sunlight, warms the atmosphere, changes winds, lifts more dust, a feedback loop, like Venus's greenhouse loop, but dusty and cold. When dust fills the air, sunlight at the surface drops, solar panels get less power, and landers get sleepy. The sky turns butterscotch. Shadows soften. The world becomes a dim, dry blur. For a rover, it is the slow dread of reduced energy. For a human, it would be a constant abrasion. Not because the wind is thick and strong like Venus, because the dust is fine and it gets everywhere, and the cold does the rest. Mars storms can last weeks. Not because Mars is dramatic, because Mars is a system with low friction and slow changes. Thin air means less damping, and dust means persistent forcing. But the truly strange part is that the wind does not need to feel strong to move dust. Dust devils on Mars leave tracks, dark streaks where they clean the surface. You can see the signatures from orbit, little spirals of cleaning, the planet wiping itself in tiny circles. And there is a sound you will not hear. Wind on Mars would be quiet because the air is thin. Even if the wind speed is high, there are fewer molecules to carry sound. A storm could look violent and yet be eerily muffled. A silent brown wall with a low hiss of sparse gas. So you have Venus, where air is heavy and sound is thick. And you have Mars, where air is thin and sound starves. Two neighboring lessons. Too much atmosphere and too little. And while you are thinking about those extremes, you remember that Earth sits in between by accident and history. Enough air to breathe, not enough to crush you. Enough greenhouse to keep oceans liquid, not enough to bake lead soft. Enough water to cycle, not enough to dissolve the continents in a week. That middle ground is not guaranteed. It is just where you happen to wake up. But the solar system does not stop at Mars. And weather gets stranger as you go outward, because once you leave the rocky worlds, you enter the gas giants. Planets without solid surfaces you can stand on, at least not in any useful sense. Weather that is not a layer above ground, but a deep, three-dimensional ocean of gas. Jupiter is the obvious monster here. A planet so big, it feels like a failed star. And its weather is not seasonal drizzle. It is bands of cloud, jet streams, storms the size of continents. If you drift toward Jupiter, the first thing you notice is scale, not a number, a feeling, like your sense of proportion is embarrassed. The planet fills your view, striped like a bruise, white zones and darker belts wrapped around a rotating sphere. Those stripes are not paint. They are circulation patterns, jets moving in opposite directions, air rising in some bands, sinking in others, different chemicals condensing at different heights, making different cloud colors. On Jupiter, clouds are not just water. High up you get ammonia clouds, pale, bright. Lower down, you get ammonium hydrosulfide clouds. Lower still, water clouds may exist. Deeper, where pressure is higher. So, you have stacked weather again, like Venus, but colder and deeper. And because Jupiter has immense internal heat, it drives convection. The planet emits more energy than it receives from the sun. It is still cooling from formation, still leaking heat. So weather is powered from within, as much as from above. This is what makes Jupiter's storms so persistent. On Earth, storms die because they hit land, lose energy, lose moisture sources. On Jupiter, there is no land to kill them, just fluid on fluid with steady energy input and little friction. And then there's the Great Red Spot, the storm you have seen in pictures, oval and brick-colored, a high-pressure system, a giant anticyclone rotating for centuries at least, a storm older than many human institutions, which is an insult to those institutions. It is like an unskippable advertisement on the face of a planet. Except the ad is for chaos, and it never ends. The red color likely comes from complex chemistry. Sunlight and charged particles break molecules apart, recombine them into reddish compounds. Organic hazes, sulfur compounds, not life, just chemistry painting the clouds. The Great Red Spot has been shrinking in recent decades, according to observations. Still enormous, still absurd, but changing. Storms merge into it, feed it, disturb it. It is a dynamic feature, not a carved landmark. If you could float near it, you would see towering cloud tops. You would see lightning in deep water clouds, likely more intense than Earth's. You would see wind shear at the edges, jets ripping past, and you would not find a calm eye you could safely admire, because there is no safe place in a storm made of hydrogen and helium. Also, you would not breathe. You would not float without a balloon the size of a city, and pressure would become a problem as you descended quickly. But you are not descending. You are observing again, because observation is cheaper than dying. Jupiter's weather is shaped by rapid rotation. A day is about 10 hours, so the Coriolis effect is strong. That creates many narrow jets, alternating directions. The planet looks striped because the atmosphere is organized into lanes, and between the lanes, storms form. White ovals, brown barges, turbulent regions, a constant churn, like boiling soup, except the soup is cold on top and hot below. And the ingredients are hydrogen, helium, ammonia, water, methane, and more. As you watch, you can feel how different weather becomes. There is no ground temperature to report, no sea level pressure, because sea level is not a thing here. Weather is the planet, all the way down until it becomes metallic hydrogen under crushing pressure. So when people ask about Jupiter weather, the honest answer is that Jupiter is weather layered on weather, a deep circulation system that you can only sample at the top. The rest you infer, like Venus, but with different tools. You can probe with gravity measurements. By tracking a spacecraft's motion, you detect slight gravitational variations. Those variations hint at how mass is distributed and how deep winds go. Juno, a modern mission, has been doing this, flying close, measuring fields. Juno showed that Jupiter's jet streams extend deep, thousands of kilometers. Not infinitely deep, but deeper than you might guess from pictures. So the stripes are not skin deep. They are part of a deep rotating fluid system. You can also measure microwave emissions that penetrate clouds. Different wavelengths see different depths. So you can map ammonia distribution below the visible cloud tops. Again, you are cheating vision using invisible waves to read a hidden structure. It is the same theme as Venus radar, just a different frequency and target. Humans cannot resist building new senses, and as you drift along Jupiter's limb, you might notice auroras at the poles, bright rings and spots, driven by magnetic fields and charged particles. Not weather like wind, but space weather interacting with atmosphere. Jupiter's magnetic field is huge, and it traps charged particles. Its moon Io spews material into a torus around the planet, feeding the magnetosphere. The result is intense radiation belts, dangerous for spacecraft. So, even in orbit, you are not safe. The planet tries to fry your electronics from a distance, like an entitled celebrity. That radiation also drives chemistry in the upper atmosphere, breaking molecules, forming hazes, affecting auroras. So weather here includes plasma physics, not just clouds. And now, speaking of moons feeding weather, Saturn enters your mind because it is Jupiter's quieter sibling, Still massive, still gaseous, but with a different aesthetic. Less bruised, more pastel. A planet that looks gentle and still would kill you efficiently. Saturn's atmosphere has banding too, but subtler. Its storms include the occasional giant outburst called a great white spot. Periodic storms that erupt and wrap around the planet in bright clouds. And then there is the hexagon at the North Pole. Yes, a hexagon. A six-sided jet stream pattern, stable for decades at least. A polygonal wave in the atmosphere. Like nature got bored and tried geometry. The hexagon is likely a standing wave in a fast-moving jet. Fluid dynamics can form these patterns under certain conditions. Laboratory experiments can create polygonal flows in rotating fluids. So Saturn is running a physics demo at planetary scale. If you could hover above it, you would see a dark central vortex surrounded by the hexagon. Clouds circulating along straight edges that are not truly straight, but appear that way. A reminder that rotation and waves can produce structure from turbulence. Saturn also has methane, ammonia, and water clouds at different depths. Its internal heat drives convection too, and lightning has been observed in Saturn storms called electrostatic discharges. The storms can be massive, with bright cloud eruptions and long-lived disturbances. Again, no land to stop them. Weather that can persist as long as energy keeps flowing. But you do not need to go deeper into Saturn tonight, because there is another kind of weather that fits your original mood. The kind that feels like a quiet appreciation for your room. And that is the weather of small bodies. Worlds with almost no atmosphere. Because once you have seen too much atmosphere and too little, you start noticing the strange calm of none. Take the moon, for example. No significant atmosphere, no weather in the usual sense, but the surface still changes. Slowly, micrometeorites hit, grinding rock into regolith. Solar wind implants ions into soil grains. Temperature swings from blistering sunlight to deep cold at night. A thermal weathering, cracking rocks by expansion and contraction. So even without air, there is a kind of weather. Not clouds and rain, but impact gardening and radiation aging. A surface being edited by space itself. Mercury too, airless, close to the sun. Extreme temperature swings. A world where the wind is mostly solar particles, where the exosphere is a whisper of atoms knocked off the surface. Sodium and potassium atoms forming a thin halo, driven by sunlight and impacts. You can call that weather if you want. A slow sputtering of atoms, a surface shedding bits into space, a planet with a breath so thin it barely counts. And now, after all those comparisons, Venus sits in your mind as a kind of anchor again. Not as the final word, but as the most familiar weirdness. The bright planet that looks calm and runs a pressure cooker under a veil. So, you let your thoughts return gently to what Venus taught you about comfort. Not emotional comfort, practical comfort. The comfort of a room temperature that does not melt solder. The comfort of pressure that does not crush. The comfort of water that falls and actually reaches the ground. And you start noticing details about Earth that are usually invisible, like how your weather is shaped by water's phase changes, evaporation, condensation, freezing, melting. Each phase change carries latent heat, moving energy around quietly. On Venus, That latent heat engine is mostly absent for water. On Earth, it is everywhere. It powers storms, fuels hurricanes, moderates temperature. It is why coastal climates are gentler than inland ones. It is why sweating works and why clouds form. Earth's water cycle is not just pretty, it is an energy transport system. And it is a geological system too. Rivers carving, sediment moving, carbon locking away. Water is the hidden machinery behind your familiar sky, which makes Venus feel like a world missing a key component, a planet that had to find other ways to move heat, other ways to cycle chemicals. So it uses thick air, global circulation, sulfur chemistry. Different machinery, different outcome. And if you keep tracing that thought, you realize that planets are not just places. They are systems of feedbacks, some stabilizing, some amplifying. Venus is what happens when amplifying feedback wins. Earth is what happens when stabilizing feedback survives. For now is doing a lot of work in that sentence. Because Earth has had near misses. Snowball episodes where ice reached low latitudes, warm periods with high carbon dioxide, and different oceans. Mass extinctions, volcanic winters, impact dust veils. Earth has never been safe. It has just been habitable often enough for you to exist. And that is not a compliment. That is a statistical fluke with good marketing. But you are still not concluding anything. You are still in the middle of the drift. So you keep it simple and you keep it sensory. You picture Earth's weather doing something Venus cannot do. A cool night. On Earth, after sunset, the ground radiates heat into space. The air cools, often from the ground up. Dew forms when surfaces drop below the dew point. Fog can pool in valleys. Cold air drains downhill like invisible water. These are small, quiet processes. You notice them in the morning chill, in the wet grass, in the mist. On Venus, the atmosphere keeps the night from being a reset. It holds heat in, spreads it around, denies the surface relief. So when you feel a cool sheet or a cool room, you are experiencing an atmospheric property. A planet that lets heat leave at night, at least partially. A sky that is not an efficient trap. And then you remember the simplest comfort of all. Rain that completes its journey. Water vapor condenses, droplets grow, they fall, they hit the ground, they soak soil, feed plants, refill rivers. They make that smell petrichor, released from dry ground by moisture. Venus has falling droplets that vanish before they arrive. Mars has water ice that sublimates and dust that dominates. Jupiter has storms without ground, lightning in deep clouds, endless churn. Earth has boring rain, and that is a luxury. So you let that appreciation sit there, quietly, without turning it into a speech. Because the point is not gratitude. The point is contrast and texture and a mind that can drift across worlds. And in that drift, Venus remains a bright dot in your peripheral imagination. Still swirling, still hiding, still doing its efficient routine. A planet with weather that never gives you the comfort of completion. You could keep listing facts and the list would never end. But the better approach is to stay inside the sensations and the mechanisms. Layered clouds, sulfur cycles, thick air circulation, slow rotation. A hidden surface mapped by echoes. A climate that might have pivoted long ago and then stayed locked in. And now, While you are still holding that, you start turning over a quieter, more technical question. How do we even define wind speed on Venus when the air is dense and slow? On Earth, wind is often described in meters per second or kilometers per hour, but what matters physically is momentum and force. A slow wind in dense air can move as much mass as a fast wind in thin air. So near Venus's surface, even a gentle breeze can push hard. That is why some lander images show little evidence of violent surface wind damage, not because the wind is absent, but because the environment is stable and heavy. Dust transport happens, but not like Earth's sandstorms. It is more like slow, persistent movement when conditions allow. Up in the cloud tops, wind speeds are high, and that is where you get the striking global patterns. The superrotation, air circling the planet faster than the surface turns. Scientists try to understand that with atmospheric waves. Thermal tides, driven by sunlight heating the atmosphere unevenly. Gravity waves, not the space-time kind, but buoyancy waves in fluid. Momentum transport, where waves deposit energy and change mean flow. It is like listening to a complicated piece of music from outside the concert hall. You hear rhythms, you infer instruments, you cannot see the musicians because the clouds are in the way. So you build models and you test them against what you can measure. The models are improving slowly, and each improvement is another small victory over a world that refuses to cooperate. The irony is that Venus is probably easier to model than Earth in some ways, because Earth has oceans, land, ice, life, and endless local variations. Venus is simpler. No oceans, no forests, no mountains interacting with moist air in the same way. A more uniform boundary condition, a more consistent circulation. So its weird weather is, in a grim sense, clean. Clean does not mean friendly. It means less complicated, more relentless. And that takes you back again to the image of the lid. An atmosphere with a planet trapped inside it. A world where the surface is not the main stage. The atmosphere is the main stage. That is a good place to pause your drift, not to end, but to pivot. Because once you accept the atmosphere as the main stage, you can start thinking about atmospheres as the true personality of worlds. Not just Venus, but anywhere. And that leads you, naturally, to ask a quiet question. What makes an atmosphere stay or leave? Why does one planet keep a thick blanket and another lose it to space? It comes down to gravity, temperature, and time. A planet's gravity holds gases like a bowl holding soup. Temperature gives molecules speed, like soup trying to boil away. And time lets tiny leaks become massive changes. Light gases, like hydrogen and helium, escape easily from small warm worlds. Heavier gases, like CO2, stick around more. But solar wind and radiation can strip atmospheres too, especially without magnetic protection. Impacts can blow parts away or deliver new volatiles. So atmospheres are not static. They are negotiated constantly. Between planet and space, Earth negotiates and keeps a breathable mix. For now, Mars lost much of its early atmosphere, leaving a thin remnant. Venus kept and accumulated until the blanket became a prison. That negotiation is the deeper weather story, because weather is what the atmosphere does day to day. Climate is what it does over centuries. Atmospheric evolution is what it does over billions of years. The longest forecast possible and the least forgiving. So you keep that in your mind as you continue traveling, not racing, not jumping, just drifting between worlds, letting each one show you a different rule. And the next rule, waiting in the dark, is about distance from the sun. Because once you go far enough out, heat becomes rare, sunlight becomes a weak rumor, and weather starts relying on internal heat and exotic volatiles. But before you reach those far worlds, you remain in this middle distance where Venus is still visible behind you, bright and steady, like a lie told calmly. And you start thinking quietly about what it would mean to visit again. Not with flesh, obviously, with smarter machines, better materials, and a little more patience. High-temperature electronics could last longer on the surface. Silicon carbide devices designed to operate at higher heat. Pressure vessels with improved insulation, maybe even mechanical computers if you feel nostalgic and desperate. Long-lived landers would let you monitor weather near the surface directly. Pressure fluctuations, wind patterns, chemical changes over days and weeks. You could listen for quakes. You could watch for subtle changes in light and haze. You could measure how the atmosphere interacts with rocks. You could also drill, sample deeper material, see if chemistry changes with depth. You could test theories about surface mineral reactions with sulfur compounds. You could look for recent volcanic deposits, fresh surfaces with distinctive signatures, but every extra hour on Venus costs engineering pain. Heat ruins lubricants, breaks seals, degrades circuits. Pressure crushes weak points. Chemistry corrodes surfaces. It is a hostile lab bench, which is why orbit and balloons remain the comfortable compromise. Distance as survival, altitude as mercy, science that floats rather than lands. You can picture a future balloon drifting in Venus's middle atmosphere, a pale sphere against pale clouds. It carries instruments like ears and noses. It samples droplets, measures gases, tracks winds. It floats in a layer where your pressure suit would not implode instantly. From that layer, Venus might feel almost ordinary. Temperatures like a warm day, pressure like Earth's. Sunlight filtered, soft. And then you look down and remember what sits beneath. A furnace under a ceiling. That contrast is very Venus. A narrow comfort zone above a lethal foundation. A reminder that habitability is often a thin line in a thick system. And speaking of thin lines, your attention starts sliding toward the outer planets again, because the solar system has more of them than you probably give it credit for. More atmospheres, more chemistry, more weather that would make Earth seem quaint. But you do not leap there yet. You let the thought form slowly, like a cloud droplet condensing. You let it gather mass, and then begin its fall. Because there is something worse than acid rain that never lands. There is weather that is so cold that the very idea of rain changes substance. Methane rain, nitrogen snow, ice that behaves like rock. And somewhere out there, beyond Saturn, beyond the warmth, there is a moon with lakes, a thick atmosphere, and a sky that rains hydrocarbons. A place that makes Venus